Have you ever wondered what truly happens inside a black hole, where light itself can no longer escape? Tonight, in Calm Science Sleep, we'll travel quietly through gravity's deepest secrets, where time slows and the universe bends into silence. Here, science unfolds softly, step by step, without rush, without noise. Stay with us until the end, and let curiosity guide you into calm. If you enjoy this gentle way of learning, please subscribe, like, and leave a comment. It helps new listeners find us and truly motivates me to create more calm, meaningful journeys. When we look at the night sky, we mostly see light. Stars, nebulae, the faint glow of distant galaxies, all of them shine because energy can escape. But somewhere among them, there are places where light cannot. They do not glow, they do not reflect, and yet their presence shapes everything around them. We call them black holes. A black hole is not an object in the ordinary sense. It has no solid surface, no boundary we could touch. It is a region of space where gravity becomes so strong that nothing, not even light, can leave once it crosses a certain point. In that sense, a black hole is the quiet extreme of nature's own geometry, a place where space and time curve back on themselves. This episode is a journey toward understanding what happens inside that invisible boundary, not through imagination or fiction, but through the steady reasoning of science. We will move step by step from the outer edges of a star's collapse to the deepest region where the known laws of physics dissolve. You may find it helpful to simply listen, allowing the rhythm of the words to unfold at their own slow pace. The story of black holes began not with observation, but with mathematics. In 1915, Albert Einstein published his general theory of relativity, describing how gravity is not a force pulling masses together, but the effective mass bending the fabric of space-time. A few months later, a German physicist named Karl Schwarzschild, serving at the front during World War I, solved Einstein's equations for the simplest possible case, a perfectly spherical mass. His result described a radius at which light could no longer escape. It was a purely theoretical finding, yet it contained the seed of the modern black hole. For decades, many scientists believed such objects could not exist in reality. They seemed too extreme, too absolute. But nature, as it turned out, was even more daring than theory. In the mid-20th century, astronomers began to detect stars orbiting invisible companions. The way those visible stars moved suggested that something very heavy, but completely dark, was nearby. Later, radio telescopes and X-ray detectors confirmed it. Collapsed stars, billions of times denser than anything we know, were scattered throughout our galaxy. The term black hole was popularized by physicist John Wheeler in 1967. It gave a name to what the equations had predicted, a region from which nothing could return. Yet the word itself can be misleading. A black hole is not a hole in space. It is a region of extreme curvature, a place where what we call space and what we call time exchange roles. To imagine what happens inside, we first need to understand how gravity behaves when pushed to its limits. Gravity is not simply attraction. It is geometry. The sun bends space-time enough to hold the planets in their orbits. A neutron star bends it far more tightly. A black hole is what happens when the curvature becomes infinite. The surface that marks this transition is called the event horizon. It is not a physical barrier, but a mathematical boundary, the point beyond which all paths curve inward. You might think of the event horizon as a silent threshold. Outside of it, we can still observe, still measure. Inside, every path leads deeper. From the outside, time seems to slow near that edge, almost to a stop. But for the object falling in, time feels normal. The crossing happens without drama. This difference, what one observer sees and what another experiences, is the beginning of many paradoxes that black holes reveal. Through this journey, we'll learn how a star becomes a black hole, how nuclear fusion, the process that balances gravity, ends when fuel runs out. When the internal pressure collapses, the core implodes, compressing billions of tons of matter into a volume smaller than a city. The outer layers are flung away as a supernova, while the remaining core sinks into itself, crossing the boundary of no return. We'll also explore how space-time behaves in the presence of such density. Einstein's equations tell us that the curvature becomes infinite at the center, a point called the singularity. Yet this infinity signals a limitation, not of nature, but of our models. It tells us that our understanding of gravity and quantum mechanics is incomplete. Black holes, in their silence, show us where knowledge ends. Inside, strange things happen to time. The closer you are to the horizon, the slower your clock runs compared to a distant one. To a faraway observer, an object falling toward a black hole appears to freeze in place, fading slowly from view. But for the falling object itself, time continues smoothly until the moment it reaches the singularity. This dual perspective challenges our most basic intuitions about reality. During this episode, we'll look at the theories that try to reconcile these contradictions. We'll meet the concept of Hawking radiation, a gentle evaporation predicted by quantum physics, through which black holes can lose energy and eventually vanish. We'll reflect on the information paradox, the question of whether information swallowed by a black hole is truly lost or somehow preserved in subtle ripples at the horizon. And we'll consider the possibility that black holes are not the end of matter, but the beginning of something new, perhaps gateways to other regions of the cosmos, or transitions where space and time reconnect in unexpected ways. Every idea will unfold calmly, without haste. Black holes invite that approach. Their existence stretches the limits of comprehension, and yet they follow simple rules written in the equations of gravity. The more we learn, the more we see that their behavior is not chaos, but structure, an order too deep for every day. Senses to grasp. It can be humbling to realize that the center of our galaxy, the Milky Way, contains a black hole 4 million times more massive than the Sun. It sits quietly, invisible, surrounded by stars that orbit it at tremendous speeds. This object, called Sagittarius A star, anchors our galaxy's rotation. Without it, the shape of the Milky Way would not be the same. Black holes are not merely destructive. They are essential to the architecture of the universe. Throughout this exploration, the tone will remain steady and clear. There is no need for drama when the facts themselves are so profound. The calm study of black holes leads us to questions about time, matter, and information, but also about perception and meaning. What does it mean for something to exist if it can never be seen? What happens to space when it bends upon itself? And what becomes of time when all motion points inward? Science cannot yet answer all of these questions, but it can guide us closer. The journey is as much about understanding as it is about humility, accepting that the universe contains regions we may never reach, but can still describe with astonishing precision. As we continue, we will move gradually from the familiar to the extraordinary, from gravity as curvature, to the birth of a black hole, to the strange behavior of time near its edge. Each step will build upon the last, forming a quiet continuum of discovery. You may notice, as we go on, that the more we talk about what disappears inside a black hole, the more we learn about what remains outside, about the way reality holds. Its balance between what is seen and what is hidden. And so, before we cross the first threshold, it's enough to understand this. A black hole is not a tear in space, nor an end of everything. It is a solution of nature, a place where the universe expresses its laws in the simplest, most uncompromising form. The rest of our journey will explore those forms in detail. The gentle geometry of gravity, the event horizon as a silent border, and the unfolding of time inside. Step by step, we will enter the calm logic of the cosmos, beginning with the force that makes black holes possible, gravity itself. To understand what happens inside a black hole, we first need to understand the quiet force that creates it. Gravity is something so familiar that it often feels invisible. It holds the oceans to the earth, guides the moon across the night sky, and gives weight to our steps. Yet it is also the architect of galaxies, the sculptor of cosmic structures, and the silent hand that determines how the universe evolves. For centuries, people imagined gravity as an invisible attraction acting between distant objects, a mysterious connection that seemed to reach across empty space. That image worked well enough for the motions we could see, but it was incomplete. It told us what gravity did, not what it was. When Isaac Newton published his law of universal gravitation in 1687, he described gravity as a force acting instantaneously between any two masses, its strength depending on their size and the distance that separated them. The law could predict the fall of an apple, the path of a cannonball, or the orbits of planets with stunning accuracy. Yet even Newton admitted that he had no idea how such a force could travel through nothingness. Hypotheses non finito, he wrote. I frame no hypothesis. For more than 200 years, his equations ruled the heavens, guiding navigation and astronomy. But the mystery of what gravity truly was remained untouched. By the beginning of the 20th century, that picture began to change. Albert Einstein, reflecting on how motion and light interact, proposed that gravity was not a force at all, but a manifestation of the geometry of space and time. In his General Theory of Relativity, published in 1915, matter and energy do not pull on each other through some invisible thread. Instead, they bend the fabric of the universe itself. Space and time are not passive stages where events occur. They are active, flexible dimensions that respond to the presence of mass. When something heavy like a planet or a star appears, it curves the geometry around it, and other bodies move along those curves. The idea can be visualized, though only imperfectly, by imagining space-time as a smooth elastic sheet. Place a heavy ball on that sheet, and it sinks slightly, creating a depression. A smaller ball rolling nearby will follow the slope of that depression, circling around it not because the larger ball exerts a pull, but because it moves along the natural curve of the surface. In reality, this curvature happens in 4 dimensions, 3 of space and 1 of time, yet the image helps convey the essence of the concept. The force of gravity is simply the motion of objects following the geometry of the universe. This shift in understanding was revolutionary. It transformed gravity from a mysterious action at a distance into an elegant consequence of shape. Einstein's field equations, compact but profound, link the curvature of space-time to the energy and momentum of matter. Wherever there is mass, there is bending, and wherever there is bending, objects follow curved paths. Even light, though massless, must obey these same rules, moving along what physicists call geodesics, the straightest possible lines in curved spacetime. Einstein's vision was soon put to the test. In 1919, during a total solar eclipse, British astronomers, led by Arthur Eddington, photographed stars whose light passed close to the sun. when they compared the apparent positions of those stars with where they appeared when the sun was elsewhere in the sky. They found that the light had shifted by precisely the amount Einstein's equations predicted. Space around the sun was not perfectly flat. It was gently curved by the sun's mass, bending the path of light itself. That observation, though subtle, confirmed that the geometry of space-time is real, not metaphorical. The discovery rippled through science and philosophy alike. It meant that the universe is not built on rigid scaffolding, but on a living geometry that changes whenever matter moves. Time itself is part of that geometry. A clock on the surface of the Earth ticks ever so slightly slower than a clock on a mountaintop because it lies deeper in the planet's gravitational field. The effect is tiny, just billionths of a second per day, but measurable, and it must be corrected in technologies such as the global positioning system. Without these relativistic adjustments, the navigation in your phone would wander by several kilometers each minute. In this way, Einstein's theory quietly shapes modern life. Every satellite, every astronomical measurement, and even the synchronization of data networks depends on our ability to account for the way gravity alters time and space. On cosmic scales, the same principle orchestrates the formation of galaxies and clusters. Massive regions of matter bend the surrounding space-time, guiding gas, dust, and stars into graceful spirals. The curvature becomes both the map and the motion, with mass and geometry locked in a delicate conversation that has continued since the universe began. To describe this mathematically, physicists use what is called the metric tensor, a set of equations that define the distances and durations between events in spacetime. When the universe is empty, this metric is flat and simple. When mass and energy appear, the metric changes, encoding how every path, every ray of light, and every tick of a clock adjusts to the new curvature. The Einstein field equations tie these changes to the distribution of energy, linking geometry and matter in a perfect symmetry. Matter tells space how to curve, and curved space tells matter how to move. This unity between mass and geometry reveals why gravity can never be truly shielded or blocked. It is not something that passes through space. It is the shape of space itself. Even a small pebble on the ground contributes a barely perceptible ripple to this geometry, though it is so faint that only the most massive objects produce measurable effects. When two neutron stars orbit one another, their combined curvature sends out waves, gravitational waves that travel across the cosmos. These waves, first detected on Earth in 2015, are minuscule distortions in space-time, stretching and squeezing distances by less than 1,000th of the width of a proton, yet they carry the history of cataclysmic events billions of years old. The detection of gravitational waves confirmed that the fabric of the universe is not static but elastic. It can tremble and resonate, conveying information in the pure language of geometry. Listening to those signals, scientists have observed the merging of black holes, collisions of neutron stars, and the final moments of cosmic systems that would otherwise remain invisible. Each vibration is a whisper of curvature reaching us through vast darkness, evidence that gravity is not a passive background, but a dynamic participant in the story of the universe. Understanding gravity this way also changes how we think about weight and motion. When you stand on the ground, you feel the earth pushing upward on you, preventing you from following the natural geodesic that your body would take through space-time. In orbit, astronauts float not because gravity has disappeared, but because they are freely following that geodesic, constantly falling toward Earth while moving fast enough to miss it. Weightlessness is not the absence of gravity. It is the purest experience of it. In everyday life, these concepts are subtle, The curvature of space-time around us is extraordinarily mild. It bends over billions of meters, yet magnified across cosmic distances or concentrated within a massive star. That same geometry becomes the decisive factor that shapes the destiny of matter. It determines how stars burn, how light travels, and how time itself flows. Einstein's equations also hinted at situations where curvature could become infinite, where mass becomes so concentrated that no known force can stop it from collapsing further. Such regions would form horizons from which nothing, not even light, could return. At first, these ideas seemed like mathematical curiosities, far removed from the physical universe. But as observations improved, astronomers began to find evidence that nature indeed creates these extremes. The thought that gravity could fold space-time so completely that it traps even light is both humbling and beautiful. It shows how the same gentle geometry that guides a falling leaf can also govern the fate of stars. The equations that explain the moon's orbit can, under greater pressure, describe the birth of a black hole. The continuum between the ordinary and the extraordinary is unbroken. Only the scale changes. You might notice, as you think about this, that gravity connects every level of existence, from the drop of rain to the spiral arms of galaxies. It is both familiar and profound, the quiet rhythm of the universe itself. Understanding it requires patience, because gravity reveals its nature not through sudden events, but through continuous, measurable patterns dotted its heart. Gravity is simplicity. Matter curves space-time, and everything, including light, follows that curvature. The entire universe operates under this rule, from the smallest particles to the largest cosmic webs. And yet, when the curvature becomes too steep, when matter pushes its own geometry beyond balance, something extraordinary begins in that moment. The delicate harmony between pressure and gravity collapses. The star that once resisted its own weight gives in, and the curvature deepens into a well from which nothing can climb. What was once gentle becomes absolute. This is where our next chapter begins, with the quiet, inevitable process through which a star's internal forces fail and gravity takes complete control. From the calm geometry of space-time, we move now toward the moment when that geometry folds inward, marking the birth of a black hole. Every black hole begins as a star. For most of its life, a star is an immense sphere of plasma held in perfect balance between two opposite forces. Gravity pulls all its matter inward, while the heat from nuclear fusion pushes outward. Deep in the core, hydrogen atoms collide and fuse into helium, releasing vast amounts of energy according to Einstein's principle that mass and energy are interchangeable. That energy radiates outward, creating the pressure that holds the star up against its own weight. As long as fusion continues, the star remains stable, shining quietly for millions or even billions of years. But fuel is finite. Over time, hydrogen in the core is consumed, and the delicate equilibrium begins to shift. When hydrogen runs low, fusion slows, gravity gains ground, and the core contracts. As it compresses, the temperature rises, igniting new reactions that fuse helium into carbon and oxygen. For stars like our Sun, this new phase is brief. The outer layers swell into a red giant, then drift away to form a glowing nebula, leaving behind a white dwarf, a dense but stable remnant roughly the size of Earth. In such stars, collapse stops because the electrons inside resist being squeezed closer together, creating what physicists call electron degeneracy pressure. Heavier stars live faster and die more dramatically. When a star has more than about 8 times the mass of the Sun, the pressures inside become extreme enough to continue fusion beyond helium, creating heavier and heavier elements, neon, magnesium, silicon, and finally iron. Each new stage happens faster than the last. Fusion of hydrogen into helium might last 10 million years, but once iron appears, everything changes in less than a second. Iron cannot release energy through fusion. It consumes energy instead. When the core becomes rich in iron, the furnace that has sustained the star shuts down abruptly. Nothing remains to oppose gravity. At that moment, collapse begins in earnest. The core's support fails, and gravity crushes it inward at a significant fraction of the speed of light. Electrons and protons merge into neutrons, releasing a flood of neutrinos that escape into space. The outer layers, suddenly without support, crash inward as well, rebound off the dense core, and explode outward in a supernova, one of the most powerful events in the universe. In a single instant, more energy is released than our sun will emit over its entire lifetime. The explosion can briefly outshine an entire galaxy, scattering heavy elements like gold, uranium, and iodine into the interstellar medium, where they will someday become part of new stars, planets, and living organisms. What remains after the explosion depends entirely on the original mass of the star. If the remnant core has between about 1.4 and 3 solar masses, the collapse stops at the neutron star stage, an object only about 20 kilometers wide, but so dense that a teaspoon of its matter would weigh billions of tons. Neutron degeneracy pressure, created by the quantum nature of matter, prevents further collapse. But if the mass of the core exceeds that limit, not even neutrons can resist gravity's pull. The compression continues without end, and a black hole is born. The formation of a black hole marks the point where the known laws of physics are stretched to their breaking limit. The entire mass of the collapsing core continues inward until all of its matter and energy are confined within a region whose escape velocity exceeds the speed of light. The boundary of that region is called the event horizon. Once the collapsing matter passes through this boundary, no information about it can reach the outside universe. To a distant observer, the collapse seems to slow and then freeze just above the horizon, its light red-shifted to invisibility. But from the point of view of the infalling material, time continues normally. It crosses the horizon in a finite moment and falls toward the center. This dual perspective, one external and one internal, is one of the most fascinating consequences of general relativity. From the outside, the dying star appears to hover forever, fading into darkness. From the inside, the story is far shorter and far more final. The matter continues inward until density and curvature become infinite, forming a singularity. Whether that singularity is truly a point of infinite compression or a region where our equations simply fail is still unknown. What is clear is that the structure of space-time has changed profoundly. The star no longer exists as a physical object. It has become a geometric feature of the universe. There are several paths to this outcome. The most common is the collapse of a massive star after a supernova, known as a stellar mass black hole. But nature provides other routes as well. In the dense environments of early galaxies, clouds of gas can collapse directly into enormous black holes without forming stars first. These supermassive black holes, ranging from millions to billions of solar masses, are found at the centers of almost all large galaxies. Astronomers believe that smaller black holes merged and accreted material over cosmic time, growing alongside their host galaxies, and shaping the formation of stars through their powerful gravitational influence. Between these two extremes, a stellar mass, and a supermassive. There may exist a third category, intermediate mass black holes, hundreds or thousands of times heavier than the Sun. Evidence for them comes from dense clusters of stars, where gravitational signatures suggest hidden masses too large to be single stars, yet too small to be galactic nuclei. Their discovery could help explain how supermassive black holes grew so quickly after the Big Bang. Each of these types shares the same defining feature. Once the event horizon forms, nothing inside can communicate with the outside universe. The horizon marks the ultimate boundary of knowledge, a surface beyond which the geometry of space and time becomes entirely inward-facing. Even light, which usually defines the boundary of what can be seen, bends back toward the center. To an observer far away, the newly formed black hole appears as a sphere of perfect darkness, surrounded by a thin ring of heated matter, still spiraling inward. That ring, or accretion disk, shines with X-rays and gamma rays as it releases the last energy of infalling material, revealing the presence of a black hole not by what escapes, but by what disappears. The birth of a black hole is both violent and silent. Violent in the sense that entire layers of a star can be blown into space at relativistic speeds, scattering elements across light years. Silent in the sense that the core itself vanishes from view, leaving behind no sound, no light, and no direct signal. Only gravity remains, continuing to shape the orbits of nearby stars and gas. Over time, the black hole may draw in more material, growing slowly, or it may wander through space almost unnoticed, a remnant of a long-dead star dot in the last few decades. Observations have provided direct evidence of these processes. In 2019, the Event Horizon Telescope produced the first image of a black hole's shadow in the galaxy. M87, a bright ring surrounding a dark center, exactly as predicted by Einstein's equations. The light from hot gas swirling near the horizon traced the outline of space-time itself. That image confirmed what theory had long suggested. Black holes are not theoretical abstractions, but real structures carved by gravity into the geometry of the cosmos dot as instruments improve. Astronomers now detect the aftershocks of black hole births through gravitational waves. When two massive stars collapse and merge, they send out ripples in spacetime that travel across the universe. The signals recorded on Earth match the final moments of collapsing cores and the formation of new black holes. Each detection tells the same quiet story: gravity, taking control when every other force has reached its limit. You might reflect that these deaths of stars are not endings in the usual sense. The elements scattered by supernova seed future generations of stars and planets. The black holes that remain become the anchors of new systems, influencing orbits, drawing in gas, and shaping the evolution of galaxies. Creation and collapse are parts of the same process, gravity reshaping matter into new patterns over cosmic time. The life of a star, from its birth in a cloud of gas to its final collapse, is an expression of balance. For most of its existence, pressure and gravity coexist in harmony. At the end, gravity wins, but the result is not destruction in the ordinary sense. It is transformation. The material world gives way to pure curvature, a region where the language of physics changes. One could say that a black hole is the universe's way of writing the word limit. It marks the boundary where the equations that describe matter must give way to the equations that describe space itself. It is the moment when the distinction between something and nothing becomes purely geometric. From here, our journey continues inward. The star has collapsed, and the event horizon has formed, a surface from which no return is possible. To explore further, we must pause at that invisible border, where light bends and time slows almost to stillness. In the next part, we will cross that threshold and examine what the event horizon truly is, not a wall, but a one-way surface that quietly separates the knowable universe from the regions beyond. A black hole does not have a solid edge. There is no surface you could touch, no shell or crust that marks its presence. Instead, what defines it is a boundary in space-time, a region where the geometry becomes so steep that every possible path curves inward. This boundary is called the event horizon. It is the quiet threshold between the part of the universe where information can still escape and the part where all trajectories, even those of light, are drawn inward forever. From far away, the event horizon behaves like a sphere surrounding the hidden singularity at the center. Its radius depends on the mass of the black hole. For a non-rotating, uncharged black hole, the simplest kind described by Carl Schwarzschild's 1916 solution to Einstein's equations, the characteristic size, called the Schwarzschild radius, grows in direct proportion to mass. If you double the mass, you double that radius. For an object with the mass of Earth, this radius would be less than a centimeter, and for the Sun, it would be about 3 kilometers. In other words, if the Sun were compressed into a sphere roughly 6 kilometers across, the escape speed at its surface would match the speed of light, and it would become a black hole. The escape velocity is the key idea. It is the minimum speed required for an object to move away from a gravitational field and never return. For Earth, that velocity is about 11 kilometers per second, easily surpassed by rockets. For neutron stars, it reaches hundreds of thousands of kilometers per second. But inside a black hole's horizon, it exceeds the speed of light. Because nothing can move faster than light, nothing can escape. The horizon, therefore, is not a physical barrier, but a boundary of possibility, the point beyond which escape no longer exists in any direction. Imagine a spacecraft approaching a black hole from a safe distance. At first, it behaves normally. Engines can maneuver, radio signals return, light travels freely. As it moves closer, gravity increases and the paths of light rays begin to bend inward. The crew can still send messages home, but the signals arrive with increasing delay, their wavelengths stretched and redshifted by the growing gravitational field. As the ship nears the event horizon, those signals slow further, fading into the infrared, then into radio, until they vanish entirely. To an external observer, it looks as if the ship freezes at the edge of the horizon, its clock slowing, its light dimming, never quite crossing. In reality, from the crew's perspective, the crossing happens smoothly and without drama. Nothing marks the boundary locally. They would not feel a wall, only an unnoticeable transition as all paths forward now lead inward. This difference between what is seen from the outside and what is experienced from within lies at the heart of relativity. Time itself flows differently depending on one's position in a gravitational field. Near the event horizon, that difference becomes extreme. To a distant observer, an object approaching the horizon seems to take forever to reach it, but the object itself experiences a finite fall. The event horizon thus represents a boundary, not just in space, but in time, a surface where perspectives diverge irreversibly. The idea that such a region could exist was once thought absurd. Even Einstein, who derived the equations that predicted it, initially believed nature would prevent such extremes. But as theoretical understanding deepened, and as astrophysical evidence accumulated, the event horizon emerged as an unavoidable feature of relativity. In 1965, the British mathematician Roger Penrose proved a series of theorems, showing that if a region of space becomes trapped by its own gravity, meaning that all possible light rays point inward, then a singularity must form, hidden behind a horizon. The logic was rigorous, leaving no escape for classical physics. Later, Stephen Hawking extended this work, demonstrating that the area of an event horizon can only increase with time, much like entropy in thermodynamics. This connection suggested that black holes are not only gravitational objects, but also thermodynamic systems. Their horizons have temperature and entropy, concepts we will revisit later when discussing Hawking radiation. For now, it is enough to note that the event horizon is not just a geometric surface. It represents deep physical laws linking gravity, energy, and information. Observationally, the event horizon defines what we can and cannot see. The material spiraling toward a black hole forms a glowing accretion disk outside the horizon. As matter falls inward, it heats to millions of degrees, emitting powerful X-rays. These emissions allow astronomers to infer the size and shape of the black hole. Yet no radiation escapes from inside the horizon itself. The darkness we observe, the shadow, captured in 2019 by the Event Horizon telescope, is not the black hole itself, but the outline of space where light is forever redirected inward. The ring of light surrounding that shadow traces photons orbiting near the point of no return, skimming the boundary before either escaping or being swallowed. The existence of this observable shadow has become one of the strongest confirmations of general relativity in its most extreme domain. The image of the black hole in the galaxy M87, followed by the more recent observation of Sagittarius A** at the center of our own Milky Way, matches theoretical predictions with remarkable precision. The brightness pattern, the asymmetry of the ring, and the diameter of the shadow all correspond to the geometry defined by Einstein's equations. The event horizon, once an abstract concept, has now become an empirical reality dot in a rotating black hole. Described by the Kerr solution, the situation grows more complex. Rotation drags space-time itself around the black hole, an effect called frame dragging. Near such an object, space behaves almost like a whirlpool, twisting light and matter around its axis of rotation. The event horizon still marks the surface of no return, but outside it lies another region called the ergosphere, where nothing can remain still relative to distant stars. Any object entering the ergosphere is forced to move in the direction of rotation, carried by the twisting of spacetime. Energy can, in principle, be extracted from this region, a process known as the Penrose mechanism. It suggests that black holes are not merely sinks of matter, but also potential engines of cosmic power. Despite these complexities, the event horizon remains simple in its definition. It is a boundary in spacetime, separating two regimes, one where paths can lead outward and one where they cannot. What makes it extraordinary is that this separation is absolute. In every known law of physics, causes precede effects. Information can move forward in time, but not backward. The horizon enforces this same directionality in space. Once crossed, every path, even for light, points inward toward the singularity. It is as if the very geometry of reality becomes one way. Physicists often describe the horizon as a null surface, meaning that the light rays defining it travel along it indefinitely, neither escaping nor falling further inward. They hover, frozen by curvature. From the outside, that frozen surface appears unchanging. Yet quantum theory tells us that it must possess microscopic degrees of freedom, bits of information encoded on its area. These ideas connect the event horizon to some of the deepest questions in modern physics. How is information preserved in the universe? Can it ever be truly lost? And if not, where does it go when something crosses this invisible boundary? The answers remain incomplete, but one thing is clear. The event horizon represents a limit of observation. It is where our measurements, our signals, and even our definitions of time lose their conventional meaning. What happens beyond it belongs to a region that no observer outside can ever experience directly. The horizon protects the rest of the universe from the singularity, acting as a veil between knowable and unknowable domains. There is something quietly elegant about this structure. Without any solid wall or physical substance, the horizon governs the dynamics of some of the most energetic phenomena in existence. It is both intangible and absolute, a mathematical surface that divides the universe into two distinct causal regions. In that sense, it is less like a physical object and more like a law, one that geometry itself enforces. You might think of it, in a single gentle metaphor, as the surface of silence, a place where everything that once had a voice in the universe falls quiet, not destroyed, but unreachable. Beyond it, time and space continue to exist, but only inwardly, without connection to the outside world. And yet, just before this silence, extraordinary things happen. As matter approaches the horizon, its energy rises, its light reddens, and time itself stretches almost beyond recognition. The closer it gets, the slower it seems to move, until motion and time merge into near stillness. This strange behavior, the dilation of time in the presence of immense gravity, is our next step in understanding what black holes do, not just to matter, but to the very flow of time itself. When we speak of time, we often imagine it as something constant, a silent rhythm that ticks equally everywhere, from the beating of a heart to the orbit of planets. For most of human history, we believed this rhythm to be universal. 1 second here was the same as 1 second anywhere else. But near a black hole, this idea no longer holds. Time itself stretches, bends, and slows in ways that defy intuition. Einstein's general theory of relativity showed that time and space are not independent. They are woven together into a single continuum, and gravity acts upon both. When a mass curves space-time, it not only bends the paths of objects, but also changes the flow of time itself. The stronger the gravitational field, the slower time passes relative to regions farther away. This phenomenon, known as gravitational time dilation, becomes one of the most striking features near a black hole dot in weak gravitational fields, such as near the Earth. This effect is tiny. A clock at the top of a mountain ticks a few microseconds faster each day than one at sea level, because it lies slightly farther from Earth's center of gravity. Yet even that minuscule difference must be accounted for in technologies like GPS satellites, whose clocks must remain synchronized with those on the ground. Without relativistic corrections, navigation errors would accumulate by kilometers within minutes. This simple example reveals how profoundly the curvature of space-time shapes the rhythm of time dot as gravity grows stronger. The stretching of time becomes dramatic. Around a neutron star, an object only a few kilometers wide, but more massive than the sun, time runs tens of percent slower than it does for an observer far away. A person hypothetically hovering just above its surface would experience minutes, while hours passed for someone watching from a distance. Near a black hole, the difference becomes far greater. Time can appear almost a stop dot to visualize this. Imagine a spacecraft slowly approaching the event horizon of a non-rotating black hole. The crew on board experiences the passage of time normally. Clocks tick, Voices sound the same, and each second feels as it always has. But to a distant observer, the ship's progress seems to slow as it nears the horizon. The signals it sends back arrive farther apart, stretched by the gravitational redshift. Its light fades from visible to red, from red to infrared, and finally to darkness. To that observer, the ship never truly crosses the horizon. It appears frozen just above it, taking an eternity to fall. This apparent paradox arises because of the way time behaves in curved spacetime. Near the event horizon, the flow of time for the falling object slows relative to the outside world, approaching zero as it reaches the horizon. But the object itself experiences no change in its local passage of time. It continues smoothly inward. Both perspectives are correct within their own frames of reference, yet they can never be reconciled. In the language of relativity, there is no single true time. Each observer follows their own. The slowing of time is accompanied by a stretching of space. Distances measured radially toward the black hole become effectively infinite from an external viewpoint. This means that to an outside observer, it takes forever for anything to reach the horizon, even though from the object's perspective, the fall takes only a finite moment. In this sense, the event horizon marks not only a spatial boundary, but also a temporal one, a surface where external time diverges. These effects are not confined to theory. They have been measured and confirmed in many contexts. Atomic clocks flown in airplanes or placed in satellites show exactly the time differences predicted by relativity. Light emitted from dense stars shifts to red wavelengths as it climbs out of their gravitational fields, consistent with gravitational redshift. Each experiment, whether on Earth or in deep space, confirms that time is elastic. It flows differently depending on where you are in the universe's gravitational landscape. Near a black hole, that elasticity becomes extreme. To imagine it is to confront how our everyday intuitions fail. Suppose two observers, one remaining far from the black hole and the other venturing close to the event horizon, could later reunite. For the traveler who approached the horizon and returned, assuming some improbable rescue, only hours might have passed. For the distant observer, centuries or even millennia could have gone by. The difference is not an illusion of perception. It is built into the geometry of reality itself. Gravitational time, dilation has profound implications for the universe as a whole. It means that near extremely massive objects, the flow of time slows compared with the cosmic average. In the vicinity of supermassive black holes, like Sagittarius A*, at the center of our galaxy, entire regions may experience time at a pace distinctly different from ours. Stars orbiting close to such objects may see the universe outside their orbit, evolve more quickly than their own local surroundings. From their perspective, the cosmos beyond the black hole's influence would seem to move in accelerated motion. The concept also has a poetic but factual symmetry. Gravity and time are inseparable. Where space curves deeply, time slows profoundly. Where the universe expands freely, time flows faster. The two are expressions of the same structure. Some physicists have even suggested that gravity itself might be nothing more than the manifestation of time differences between neighboring regions, a large-scale effect of clocks running at different rates. While this view is still speculative, it reminds us how intertwined space and time truly are. The stretching of time also defines the boundary of observation. Because light emitted from near the event horizon becomes infinitely red-shifted, an external observer never receives the final signal. The image of anything falling in becomes a fading memory, smeared over time. For astrophysicists, this means that the visible edge of a black hole is effectively a time horizon as well as a spatial one, a region where events slow so much that they are never completed in our frame of reference. The black hole, from our point of view, is always in the process of formation, never quite finished, even though in its own frame. The collapse has long since completed. This realization touches one of the deepest insights of relativity, that time is not an absolute backdrop, but part of the dynamic fabric of the universe. It can stretch, twist, and even, in extreme cases, appear to halt. The clocks carried by observers are not measuring something external. They are tracing their own paths through curved space-time. Each clock follows its own rhythm, and none is more real than another. The idea that time could slow to such extremes challenges not only our sense of physics, but also our sense of existence. For the falling object, everything proceeds normally, no pause, no sudden stop. Yet to the rest of the universe, it becomes a frozen image, an eternal descent. In a way, a black hole contains countless such frozen stories, layers of time stacked infinitely close together at its horizon. Each represents an event that has fallen in but never finished falling. At least from our perspective outside, this image, while mathematically precise, also carries a quiet metaphor, the black hole as a place where time itself comes to rest. Not destroyed, but stretched so far that motion and duration lose distinction. In that infinite dilation lies both the limit of observation and the beginning of mystery. Still, for the matter that continues inward, time has not ended. Inside the horizon, all paths lead toward the singularity. There, the roles of space and time begin to merge and exchange. The inward direction of space becomes indistinguishable from the forward flow of time. This transformation, the gradual turning of space into time, is one of the strangest aspects of a black hole's interior. It means that once something crosses the horizon, its fall is as inevitable as the passage of moments in ordinary life. Movement toward the singularity is not optional. It is the temporal destiny written by geometry. For now, what we can say with confidence is that gravitational time dilation is real, measurable, and profound. It demonstrates that time is not an independent river flowing evenly through the cosmos, but a dynamic property shaped by mass and energy. Each black hole is therefore not just a region of extreme gravity, but also a region of extreme time. As we move deeper into this journey, we leave the domain of slowing clocks and stretched seconds, and we approach the point where the difference in gravity between two ends of a single object becomes immense. Space and time will no longer stretch uniformly, but unevenly, producing forces that test the limits of matter itself. In the next section, we will explore this phenomenon, known scientifically as tidal acceleration, through a calm and factual description of what happens when matter is gently or relentlessly pulled apart near a black hole. The closer something comes to a black hole, the stronger gravity becomes. Yet it does not grow stronger in the same way everywhere. The pull at one point in space can differ slightly from the pull at another nearby point, and this difference, known as tidal force, is what eventually stretches and compresses matter. Near ordinary planets, tidal forces are mild. They lift the oceans on Earth, creating tides that rise and fall with the moon's orbit. Near a black hole, however, those forces become so intense that they can reshape even the structure of atoms. Physicists sometimes call this process spaghettification. The name sounds whimsical, but it describes a real and measurable effect predicted by the equations of general relativity. It is the result of a simple fact. Gravity's strength changes with distance. The side of an object closer to the black hole feels a slightly stronger pull than the far side. The closer the object gets, the greater this difference becomes. The result is stretching along the direction toward the black hole and compression in the perpendicular directions, forming a long, narrow shape, like a thread drawn out of matter itself. To understand how this works, we can recall that gravitational acceleration around a massive body follows the inverse square law. The strength increases in proportion to 1 over the square of the distance. Near the Earth, that gradient is small, about 1/10,000,000th of a g between your head and your feet. Near a black hole, it grows exponentially. For a stellar mass black hole, the difference in gravitational acceleration between a person's head and feet, just seconds before crossing the event horizon, would exceed 10 trillion Gs. No material, biological or otherwise, could resist such a gradient. For a supermassive black hole, the picture changes. Because its horizon lies much farther from its center, the gradient across a human-sized object would be far smaller. In fact, one could cross the event horizon of a black hole with millions of solar masses without immediate harm, at least for a time. The stretching would be gentle, the forces imperceptible, until the journey continued deeper within. This is one of the strange symmetries of nature. The larger the black hole, the calmer its edges. Only near the smaller ones does gravity's gradient become instantly fatal. Tidal forces are not unique to black holes. We observe them throughout the universe. The planet Jupiter, for instance, exerts powerful tides on its moon Io, heating it internally and driving constant volcanic eruptions. Galaxies passing near each other experience tidal stripping, where their stars are pulled into long, luminous tails. The same mathematics describes all of these effects. Only the intensity changes. A black hole is simply the most extreme example. Gravity focused to its ultimate precision. The stretching of matter near a black hole can be analyzed quantitatively. If we consider a small object of length L approaching a black hole of mass m, the tidal acceleration between its near and far sides is roughly delta A, approximately equals 2 gml r cubed, where r is the distance from the black hole's center. As r decreases, this differential acceleration grows faster than the overall pull of gravity itself. The closer you get, the more the difference dominates, until it becomes the defining physical reality of that region. In this regime, gravity is no longer experienced as a simple attraction, but as a continuous deformation of space and matter dot in the early stages of approach. This stretching acts gently. At great distances, the object simply feels an increasing gravitational field. As it falls deeper, however, the differences become severe enough to overcome molecular bonds and atomic forces, and finally, even nuclear cohesion. The atoms elongate into thin chains of subatomic particles, each following its own geodesic toward the center. In theory, even light experiences an analog of this effect. Beams emitted radially inward converge, while those emitted tangentially are bent back. Everything, including space itself, is drawn into the same narrowing funnel. Though it sounds catastrophic, the physics behind spaghettification is elegant and predictable. It is the manifestation of differential geometry at work, the change in curvature across a finite distance. Every particle, every bit of matter follows the curve assigned to it by Einstein's equations. The process is not chaotic. It follows strict mathematical order. From an external viewpoint, the destruction of the object seems to take forever, slowed by time dilation. To the falling object, the process is finite and complete, yet smooth within its own frame of reference. There is no sudden shattering, only continuous elongation. As distances along the direction of fall grow and cross-sections shrink, laboratory experiments have, of course, never replicated such conditions. But simulations of tidal disruption around black holes confirm the theory with precision. When stars venture too close to supermassive black holes, astronomers observe brilliant flares of ultraviolet and X-ray light. These emissions occur as the star is torn apart by tidal forces. Half of its material escapes into space, while the rest spirals inward, forming a temporary accretion disk. The resulting event, called a tidal disruption flare, can outshine an entire galaxy for months. Observations of these flares match the predictions of spaghettification at stellar scales, providing direct evidence that gravity behaves exactly as relativity foresees. Despite the dramatic imagery, the deeper lesson of spaghettification is not about destruction, but about structure. It shows that gravity is not a single force acting uniformly, but a gradient, a measure of change. Without these gradients, planets would not orbit, galaxies would not form, and the universe would lack the texture that gives it shape. The same mathematics that stretches matter near a black hole also governs the gentle tides that stir Earth's oceans. At every scale, gravity reveals itself through differences. There is also a subtle connection between tidal forces and the flow of time. Because time passes differently at different distances from the black hole, each part of a stretched object experiences its own rate of time. The head and the feet, if separated vertically, would not only be pulled apart in space, but also fall out of sync in time. This divergence of clocks contributes to the overall distortion, a reminder that space and time respond together to curvature. In relativity, stretching in one implies stretching in the other. Physicists sometimes analyze these forces using the concept of geodesic deviation, which describes how nearby trajectories in curved spacetime move relative to one another. Two objects falling side by side toward a black hole will initially accelerate together, but as they descend, their paths converge. The rate of convergence measures the local curvature, in essence, how the geometry itself focuses motion. In extreme cases, those geodesics intersect, compressing the infalling matter into a single, infinitely dense line at the singularity dot in this sense. Spaghettification is the visible manifestation of the invisible geometry of space-time. It makes curvature tangible. It reminds us that gravity is not something imposed from outside, but the shape of the universe expressing itself. Each stretch, each compression, is geometry in motion. If we imagine this calmly, the process becomes less violent and more inevitable. It is the continuation of the same logic that governs every orbit and every fall. The difference is only one of degree. Matter does not resist. It follows the path set by curvature until the distinction between object and space ceases to exist. One could say, in a quiet metaphor, that spaghettification is gravity's final choreography, the last dance of matter before it becomes part of geometry itself. From the scientific viewpoint, this process also connects directly to one of the greatest puzzles in modern physics, the fate of information. If everything that falls into a black hole is stretched, compressed, and ultimately absorbed, what happens to the information contained in its structure? Does it vanish, violating the principle that information in the universe must be conserved? Or is it somehow preserved, encoded on the surface of the horizon? To explore that question, we move from the physical to the conceptual, from the measurable stretching of space and time to the invisible accounting of information. In the next section, we will look at this mystery, known as the information paradox, and examine how physicists try to reconcile the laws of quantum mechanics with the unyielding geometry of general relativity. When something falls into a black hole, it seems to vanish completely. No light, no signal, no trace escapes past the event horizon. For a long time, scientists assumed this disappearance was absolute, that matter crossing the horizon was lost to the outside universe forever. But physics, as we understand it, has a deep rule. Information cannot be destroyed. Every interaction, every state of matter, should in principle be reversible. If we could rewind the universe to an earlier moment, everything that exists now should unfold back into what it once was. This idea is not philosophical. It is part of the mathematical foundation of quantum mechanics. And that is where the paradox begins. In the 1970s, Stephen Hawking combined general relativity and quantum field theory to study what happens at the edge of a black hole. His calculations revealed something unexpected. Black holes are not perfectly black. Quantum fluctuations near the horizon cause pairs of particles to appear spontaneously. One falls inward while the other escapes outward. The escaping particle carries energy away, meaning that the black hole loses a tiny amount of mass. Over immense timescales, this process causes the black hole to evaporate. This faint emission is now known as Hawking radiation. At first, this seemed like an elegant bridge between quantum physics and gravity. But when Hawking followed the equations to their conclusion, he realized that the radiation emitted carried no information about the material that had fallen in. It was purely thermal, random in nature, like heat emitted by a hot stove. When the black hole eventually evaporated completely, all the information about its contents would be gone. To most physicists, this outcome was impossible. If information could vanish, the fundamental symmetry of quantum mechanics would break. The laws describing the universe would lose their capacity to predict the future from the past. This tension between relativity and quantum mechanics became known as the black hole information paradox. At its heart lies a conflict between two descriptions of reality. Relativity says that once matter crosses the event horizon, it is trapped forever, cut off from the rest of the universe. Quantum mechanics says that every interaction must leave a trace, encoded in some physical form. Both theories work perfectly within their own domains, yet they contradict each other at the horizon. For decades, scientists debated how to resolve this contradiction. Some proposed that information truly disappears, that the laws of quantum mechanics must be modified in extreme gravitational conditions. Others argued that information must somehow escape, hidden in subtle correlations between the outgoing radiation particles. Neither side could yet prove its case, but the paradox inspired one of the most productive lines of inquiry in modern theoretical physics. To understand why information matters so deeply, it helps to recall that in physics, information does not mean words or thoughts. It refers to the precise arrangement of matter and energy, the total record of all quantum states that define a system. When a book burns, its paper and ink turn to smoke and ash, yet the information is not lost. It is dispersed among countless atoms and photons. In principle, if we could track every particle and its motion, we could reconstruct the book completely. Hawking's paradox suggests that inside a black hole, that reconstruction becomes impossible, that the information ceases to exist in any form. This would be the only process in nature that erases data entirely. Gradually, new ideas emerged. One of the first came from physicists Jacob Bekenstein and Stephen Hawking themselves. Bekenstein noticed that a black hole's entropy, its measure of hidden information, seemed to be proportional not to its volume, as one might expect, but to the area of its event horizon. That discovery hinted that the information about everything that falls in might be stored on the surface of the horizon itself, encoded in quantum degrees of freedom too fine to measure directly. This principle later evolved into what we now call the holographic principle, the idea that the three-dimensional contents of a region of space can be described by information written on its two-dimensional boundary dot in the 1990s. Theoretical advances in string theory strengthened this possibility. Physicists Juan Maldacena and others discovered mathematical correspondences, particularly the so-called ADS-CFT duality, suggesting that the behavior of gravity in a curved space could be fully described by a quantum theory on its boundary, without gravity at all. If that duality holds universally, then information is never lost. It simply changes form. From the perspective of the external universe, what falls into a black hole leaves a quantum imprint on its surface, which gradually re-emerges through the pattern of Hawking radiation. The information is scrambled, not destroyed. Still, this picture raises new questions. If information is encoded on the event horizon, what does an infalling observer experience? From their viewpoint, nothing unusual happens at the horizon. They cross it freely, continuing inward. From the external viewpoint, the same matter appears frozen at the edge, smeared into quantum fluctuations. Two realities seem to coexist, one falling in, one remaining on the surface. This coexistence violates no mathematical law, but it challenges our understanding of what it means for something to exist. To resolve this tension, some physicists have proposed that the black hole's horizon is not a smooth surface after all. Instead, it might be surrounded by an energetic boundary, a so-called firewall that burns up information as it tries to cross. Others disagree, arguing that such a boundary would contradict the very foundations of relativity, which demand that an infalling observer experience nothing special at the horizon. The debate remains open, illustrating how the information paradox continues to push at the edges of modern physics. Despite these disagreements, one broad consensus has emerged. The universe appears to conserve information at every level. Quantum theory, with all its complexity, has never shown a violation of that principle. Most physicists now suspect that the paradox is not a failure of conservation, but a reflection of our incomplete understanding of space-time at quantum scales. To solve it fully, we may need a quantum theory of gravity, a framework that unites the microscopic laws of particles with the macroscopic curvature of the universe. Recent progress hints that this unification is not entirely out of reach. In 2019 and 2020, several research groups used simplified models of black holes to show how information might leak out gradually, encoded in subtle quantum correlations between emitted particles. Their results matched predictions from the holographic principle, suggesting that even Hawking radiation could, in theory, carry information, though in a form so scrambled that it would be unrecognizable. If confirmed, these insights would mean that no data is truly lost, only hidden within patterns too intricate for current physics to decode. This evolving view of black holes has shifted how we think about the universe itself. It implies that reality might fundamentally be informational, that matter, energy, and even space-time arise from relationships between bits of data. In this perspective, the cosmos is not a collection of objects, but a vast network of interactions, where every exchange of energy records a trace. A black hole, then, is not an eraser of information, but a processor, a region where information is transformed into new forms and returned, eventually, through radiation and gravitational waves. The information paradox reminds us that knowledge in physics is never static. Each answer leads to deeper questions, connecting fields once thought unrelated: thermodynamics, quantum theory, relativity, and information science. The mystery that began with Hawking's equations has become a bridge between worlds of theory, drawing scientists toward a single framework that could describe everything from the birth of the universe to its quiet end. There is a quiet beauty in this pursuit. It shows that even where light cannot escape, knowledge can. Ideas continue to move outward, illuminating what once seemed absolute darkness. In that sense, the black hole is both a mystery and a teacher, revealing that the limits of observation are not the limits of understanding. From this point, our exploration naturally turns to the mechanism that began this paradox, the faint radiation predicted by Hawking himself. If black holes emit energy, then they also lose mass, evolve, and over time may disappear entirely. The next part of our journey looks closely at this phenomenon, how light, born from the quantum vacuum, can escape from the edge of darkness. When physicists first described black holes, they imagined them as perfectly one-way systems, regions that could absorb anything but never give anything back. According to the classical picture of general relativity, once matter or light crossed the event horizon, its energy became part of the black hole's total mass, and nothing within the known laws of physics could reverse that process. The boundary was absolute, a place where motion and energy simply stopped contributing to the visible universe. Yet nature, as later discovered, is rarely so absolute. It tends to preserve balance, even in its most extreme forms. And in the early 1970s, that balance began to reveal itself through a new and unexpected insight into how quantum fields behave at the very edge of a black hole. Stephen Hawking's work began with a simple question: what happens to the quantum vacuum near the horizon? In quantum theory, empty space is not truly empty. It seethes with fleeting pairs of particles and antiparticles that constantly appear and vanish, borrowing energy from the vacuum in accordance with the uncertainty principle. Normally, these pairs annihilate almost instantly, restoring the balance of zero energy. But Hawking realized that near the boundary of a black hole, the immense curvature of space-time could separate these partners before they had the chance to meet again. One particle could fall inward while the other escaped outward, carrying a tiny amount of energy away. To an observer far from the black hole, that escaping particle would appear as radiation emitted from the darkness itself. This idea, which began as a mathematical exercise, transformed our understanding of black holes. It implied that they are not eternal. They can radiate energy, cool, and eventually evaporate. The rate of emission is unimaginably small for astrophysical black holes. The temperature of a stellar mass black hole is far below that of the cosmic microwave background, but for smaller, hypothetical ones, the effect becomes significant. Over vast periods of time, the black hole loses mass, shrinking slowly as it emits this faint radiation, until, in the final stages, it disappears entirely in a last, brief burst of high-energy particles. What makes Hawking radiation so remarkable is that it arises from the combination of two great frameworks of physics: quantum field theory, which governs the microscopic world of particles, and general relativity, which describes the geometry of spacetime. Individually, these theories are consistent and predictive, but when combined near the horizon, they produce results that neither could have anticipated alone. The boundary of a black hole, once thought to be a static surface, becomes a dynamic region where the quantum vacuum interacts with gravity's curvature, turning the geometry of space itself into a source of energy. To describe this interaction qualitatively, one can imagine that the gravitational field near the horizon distorts the normal symmetry of the vacuum. Virtual particles that would otherwise annihilate become real because the horizon prevents their reunion. The particle that falls inward carries negative energy relative to the outside universe, effectively reducing the black hole's mass. The escaping particle, now free, moves outward as part of a slow thermal emission. Although the radiation appears featureless, its spectrum depending only on the black hole's mass, charge, and rotation. The process connects every quantum fluctuation at the horizon with the gradual evolution of the black hole itself. When Hawking first published these results, many physicists were skeptical. The concept of a black hole radiating like a warm body seemed to contradict the entire idea of a region from which nothing could escape. Yet the mathematics was solid, and independent analyses confirmed it. Over time, the idea became one of the cornerstones of modern theoretical physics. It revealed that black holes are thermodynamic systems with well-defined temperature and entropy, obeying laws analogous to those of ordinary heat engines. The event horizon's surface area corresponds to entropy, its curvature to pressure, and the emission of radiation to a slow conversion of mass into energy. In this view, black holes participate fully in the universal flow of energy and information, rather than existing as isolated endpoints. Realization deepened the mystery rather than resolving it. If black holes emit thermal radiation, then they also emit information, or at least appear to. Yet the radiation's random nature suggested that whatever detail fell into the black hole was lost in the process. Hawking himself argued for many years that the information was destroyed, leading to the paradox described earlier. Later research, supported by developments in quantum gravity and holographic theory, pointed toward a different conclusion. The radiation might indeed contain subtle correlations encoding all the information, but so deeply scrambled that it could never be reconstructed by practical means. The universe, it seemed, could preserve its bookkeeping even when its pages appeared blank dot, although Hawking radiation has never been directly observed. Its intensity for known black holes is far below the sensitivity of any instrument. Indirect evidence supports its reality. Analog systems created in laboratories, such as sonic black holes in ultra-cold gases or optical analogs in nonlinear media, reproduce similar effects. In these experiments, waves trapped by artificial horizons emit faint radiation with the same spectral signature predicted by Hawking's equations. The results suggest that the process is not unique to gravity itself, but a general feature of horizons in any field theory, wherever information flow becomes one-way. The quantum vacuum finds a way to restore symmetry by radiating energy outward. On a cosmic timescale, Hawking radiation implies that even the most massive black holes are temporary. Supermassive black holes, weighing millions or billions of solar masses, will take unimaginable epochs, more than 10 years, to evaporate completely. Long after the last stars have burned out, when the universe is dark and cold, these black holes will remain as the final luminous sources, releasing the last energy of creation. The idea transforms our picture of cosmic destiny. Instead of ending in eternal darkness, the universe may fade gently through the slow whisper of evaporating black holes. There is an elegance in the symmetry of this process. Matter that once collapsed inward eventually returns to the universe as pure radiation. Energy and information circulate rather than terminate. The black hole becomes not a grave, but a phase, one stage in the continuous transformation of the cosmos. In a quiet sense, it is nature's way of ensuring that even in perfect darkness, balance remains. For physicists, Hawking radiation provides a rare bridge between the microscopic and the cosmic. It links thermodynamics, quantum theory, and relativity into a single framework. The entropy of the horizon, proportional to its surface area, suggests that the fundamental degrees of freedom of spacetime may themselves be two-dimensional, encoded on surfaces rather than volumes. This idea, the holographic principle, extends far beyond black holes, influencing how scientists think about the fabric of the universe itself. If every region of space can be described by data on its boundary, then our own cosmos might be a vast projection of underlying quantum information. The black hole, once a mystery of collapse, becomes a model of how reality could be constructed. The insight that radiation arises from the geometry of spacetime also changes how we view emptiness. The vacuum is not a void, but a medium filled with potential energy. Gravity, by shaping that medium, can release energy from nothing more than its curvature. This connection between shape and energy is one of the quiet triumphs of modern physics. It suggests that creation and destruction are not opposites, but complementary processes governed by the same underlying symmetries. Even Hawking, who spent much of his life refining the theory, considered its implications astonishing. It meant that the most powerful objects in the universe are also the most delicate, gradually dissolving through a mechanism born of the smallest sails. In his later work, he described black holes not as traps, but as fountains of information, structures that may eventually release everything they once absorbed, though in forms we have yet to decode. In a way, Hawking radiation blurs the distinction between inside and outside, between the known and the hidden. The boundary that once seemed absolute becomes porous at the quantum level. The black hole breathes, ever so slowly, exchanging energy with the universe. Its darkness is no longer final. It glows faintly with the memory of everything it has consumed. If we think of this process not as a paradox, but as a dialogue between gravity and quantum physics, we can see it as the universe teaching us about its own consistency. The equations that describe the birth of stars and the decay of particles are written in the same language. Hawking radiation is the punctuation that joins them. The story of a black hole, from collapse to evaporation, is the story of symmetry carried to its limit and then quietly restored. And yet, as the radiation continues and the black hole shrinks, something deeper emerges. The density and curvature near its center grow beyond measure, until the mathematics itself ceases to describe what lies within. This is where our present knowledge ends, at the point we call the singularity. To move further, we must follow gravity to its final expression, where time and space converge into a single undefined state. As we move beyond the event horizon, the familiar structure of space and time begins to lose meaning. Every direction that once seemed open now curves inward, and every path leads toward a single, unavoidable destination, the center of the black hole. According to Einstein's equations, all of the mass that formed the black hole and everything that has fallen into it since is ultimately compressed into an infinitely small point of infinite density. This theoretical point is called a singularity. It is the place where the known laws of physics cease to function, where curvature becomes infinite and time, as we understand it, comes to an end. The concept of a singularity does not refer to a physical object, but to a breakdown in our description of reality. In mathematics, a singularity appears when a quantity that should remain finite becomes unbounded, when equations yield infinities that cannot be interpreted. In the context of general relativity, it marks the limit beyond which the geometry of spacetime can no longer be defined. The equations that so beautifully describe orbits, horizons, and curvature collapse under their own weight. They tell us that the gravitational field becomes infinitely strong, that all distances shrink to zero, and that no further prediction is possible. Yet those infinities are signals, not answers. They tell us where our models end and where new physics must begin. The idea of the singularity emerged naturally from Einstein's theory, though it was resisted at first. Early researchers believed that the extreme solutions describing total collapse must be mathematical curiosities rather than physical realities. They assumed that nature would find a way to avoid infinities, perhaps through internal pressure, turbulence, or other stabilizing mechanisms. It was not until the 1960s that Roger Penrose and Stephen Hawking proved that singularities are not exceptions but inevitable consequences of general relativity under certain conditions. If enough mass is concentrated within a small enough region and no opposing force can counter gravity, collapse must continue until space-time itself ends. The theorems showed that singularities are not rare. They are built into the fabric of Einstein's equations. Inside a black hole, all paths, all possible directions lead to that final region. Unlike the center of an ordinary planet, which can be approached and described, the singularity is hidden behind the horizon. No signal can emerge from it, and no observation can reveal its structure. This makes it both central and inaccessible, the heart of the black hole, yet forever beyond view. From the outside, the singularity's presence is felt only through its gravitational field. Everything we can measure, the motion of stars, the bending of light, the slow precession of orbits, depends only on the mass, spin, and charge of the black hole, not on the details of what lies within. This property, captured by the phrase "black holes have no hair," reflects the simplicity of their external appearance. Regardless of how they form, all black holes of the same mass and spin look identical from the outside. The singularity challenges not only our equations, but also our concepts of space, time, and causality. Within that region, distances and durations lose their usual meaning. The coordinate system used to describe the outside universe fails, and even the distinction between before and after dissolves. In relativity, time is just another dimension of geometry, and when geometry breaks down, time cannot survive independently. Near the singularity, space and time merge into a single undefined continuum, and the flow of events becomes indistinguishable from the structure of the space itself. It is not that time stops. Rather, it ceases to be a direction that can be followed. Physicists generally agree that the singularity predicted by general relativity cannot be the full story. Infinite density and curvature are not physical quantities that can exist in nature. They are indications that the theory is incomplete. General relativity treats gravity as the curvature of a smooth continuum, while quantum mechanics tells us that nature at small scales is discrete and probabilistic. Somewhere between those two domains, at distances near the Planck length, around 10 to the minus 35 meters, the smooth fabric of spacetime must give way to a quantum texture. In that microscopic regime, the gravitational field should fluctuate, and the notion of a precise point becomes meaningless. The true core of a black hole is therefore not an infinite singularity, but an unknown state where quantum gravity rules. Many attempts have been made to describe what happens in that regime. String theory suggests that the fundamental constituents of reality are not points, but tiny vibrating strings or membranes, which cannot collapse to a true zero size loop. Quantum gravity proposes that space itself is made of finite loops of geometry, forming a network that resists infinite compression. In both pictures, the singularity is replaced by a region of extreme but finite density, a quantum bridge rather than an end. These ideas remain theoretical, but they share a single message. Infinity is a signpost, not a destination. What lies beyond that signpost is an open question. Some models predict that the core of a black hole might connect to another region of spacetime, perhaps even another universe, through a structure known as a wormhole. Others suggest that the collapse might rebound at the smallest scales, creating a new expansion phase, like a miniature Big Bang. In this view, every black hole could contain the seed of a new cosmos, with its own time and dimensions unfolding beyond our reach. Such scenarios are speculative, but they show how deeply the singularity touches the boundaries of cosmology. The same equations that describe the beginning of the universe also describe its deepest interiors. The singularity inside a black hole mirrors the one at the origin of time. The comparison between the cosmic singularity of the Big Bang and that inside a black hole is more than poetic. Both represent limits of prediction, points where energy and curvature reach extremes that no current theory can handle. In the early universe, the singularity gave rise to expansion and time. In a black hole, it marks their apparent conclusion. Together, they form the two poles of cosmic evolution, one creative, one absorptive, linked by the same mathematics. Understanding one may eventually explain the other. Although we cannot see or probe the singularity directly, its influence extends outward. The geometry of the space-time around it determines the orbits of matter, the formation of jets, and the gravitational waves emitted when black holes merge. In that sense, the singularity shapes the observable universe without ever being observed itself. It is the invisible center of cosmic architecture, a hidden boundary where theory meets uncertainty. One might imagine, in a soft metaphor, that the singularity is the punctuation mark of the universe's language, the place where sentences end, yet meaning continues between the lines. It does not erase what came before. It gathers it into a point of potential, waiting for a new grammar of physics to unfold. The study of singularities has led physicists toward that new grammar. By examining where relativity breaks, they can identify what a future theory of quantum gravity must accomplish. It must describe how space and time behave when curvature becomes extreme, how information is preserved, and how the continuity of cause and effect survives. Progress in this direction is slow but steady. Each new idea, from holography to loop quantum gravity, attempts to reconcile the infinite with the finite, the continuous with the discrete. In this ongoing search, the singularity serves as a guidepost. It reminds us that the universe, though vast and comprehensible in many ways, still contains regions that defy our intellect. A black hole does not end in darkness. It ends in a question, one that connects the smallest scales of quantum theory with the largest scales of cosmic evolution. As we continue our journey inward, the concept of a singularity naturally leads us to a deeper question. If space and time lose meaning there, what becomes of time itself? Does it stop, reverse, or transform into something else entirely? To approach this next idea, we must look closely at how time behaves inside the black hole, where all motion, all sequences of cause and effect, converge toward one inevitable direction. Inside the event horizon, space and time trade roles. What we once experienced as distance becomes duration, and what we once thought of as a moment becomes direction. The geometry of space-time is so radically curved that every possible path forward in time leads inevitably inward, toward the singularity. There are no stationary points, no stable orbits, no way to turn back. The concept of falling ceases to describe a spatial motion. It becomes a passage through time itself. In this domain, the end of space and the end of time are not separate events, but aspects of the same geometry. In general relativity, time is not a universal flow, that moves uniformly everywhere. It is a dimension that depends on gravity, velocity, and curvature. Near a black hole, this dependence reaches its extreme. Once an object crosses the event horizon, its future is no longer open in multiple directions. All time-like paths, all routes consistent with the forward movement of cause and effect, converge on the singularity. To move forward in time, inside a black hole, is to move toward that central point. There is no other choice, no alternate future, no trajectory that avoids it. This inevitability can be difficult to visualize, because we are used to thinking of time as something external, a clock ticking regardless of where we are. But in relativity, time is part of the structure of the universe itself. It bends, stretches, and aligns with the gravitational field. The same equations that describe how light curves around a massive star also describe how moments stretch and compress. Near the singularity, that curvature grows so intense that time's direction becomes indistinguishable from the spatial inward direction. The singularity is therefore not only a place of infinite density, but also the endpoint of every possible timeline within the black hole dot if we could observe an infalling object from a safe distance. Its behavior would appear paradoxical. From the outside, time slows for the falling object until it seems frozen just above the horizon. Yet for the object itself, time continues normally. Seconds pass, events unfold, and the singularity draws closer. Inside the horizon, this pattern continues. Time flows smoothly for the traveler, but every moment carries them closer to the center. The geometry dictates that progress through time is equivalent to movement toward the singularity. It is not a matter of acceleration or speed. It is simply the structure of causality. Mathematically, this can be understood through the behavior of light cones, diagrams, that represent the possible directions in which cause and effect can propagate. Outside the black hole, these cones point partly outward, meaning that signals and matter can still move away. At the horizon, the cones tip inward, aligning with the boundary itself. Inside, they tilt completely, pointing only toward the singularity. Every particle, every photon, every thought follows these cones, because they define the local meaning of future. Thus, the end of space within a black hole is also the inevitable end of time. For the infalling observer, nothing marks this transformation. They would feel no barrier or threshold, no sudden change in the rhythm of their own clock. The experience would seem normal until very near the singularity, the gravitational gradient became so steep that tidal forces overwhelmed every form of structure. The compression of space and the distortion of time would merge, dissolving any distinction between the two. The laws that govern atoms and molecules would no longer apply, because those laws depend on a background of stable spacetime. Where that background disappears, so does the meaning of continuity. In this sense, the end of time is not an event that occurs after a sequence of moments. It is the limit of what can be described as moments at all. It marks the point where the progression of causes and effects, which defines physics itself, comes to an end. The singularity represents not just the boundary of the universe's map, but the boundary of its logic. When general relativity reaches this limit, it does not tell us what lies beyond. It simply falls silent. Still, this silence does not necessarily mean nothing exists there. Most physicists believe that the infinities of classical relativity are signs that quantum effects must intervene. At the smallest scales, space and time are expected to fluctuate, becoming granular rather than continuous. In such a regime, the sharp boundary at the singularity might blur, replaced by a region where quantum geometry takes over. Instead of an end of time, there could be a transformation of time, a phase where our ordinary sense of sequence is replaced by something more fundamental, perhaps a network of probabilities or discrete transitions between states. Some theoretical models propose that inside a black hole, time might curve back on itself or branch into new dimensions. In these scenarios, the singularity is not a single point, but a region of quantum connections, linking different areas of the universe, or even different universes. Others suggest that the collapse of matter may trigger a bounce, reversing at the Planck scale and giving rise to a new expansion. In such a picture, what we call the end of time inside a black hole could correspond to the beginning of time in another cosmos. The death of one space-time becomes the birth of another. These ideas remain speculative, but they reflect an underlying consistency. Physics resists finality. Every time theory reaches a wall, it hints that another structure may exist on the other side. The same was true when classical mechanics gave way to quantum mechanics, and when Newtonian gravity was replaced by general relativity. Each new framework preserved the older one as a limit while expanding its scope. In the same way, a future theory of quantum gravity may show that what we now call the end of time is simply the edge of our understanding. From a broader perspective, this boundary forces us to reconsider what time truly is. We treat it as something that flows, but in physics, time is more accurately seen as an ordering of events, a structure linking cause and effect. If that order ceases to exist, then time has fulfilled its role. Inside a black hole, that fulfillment is total. Every particle reaches its destination, every trajectory its conclusion. The universe inside becomes a record without future frames. The idea that time can end is unsettling because it conflicts with experience. Yet even outside black holes, time is not absolute. The expansion of the universe, the evolution of entropy, and the motion of galaxies all reflect processes that have beginnings and ends defined by geometry. On cosmological scales, time is as local as gravity itself. In the same way that space can curve, time can begin, stretch, and eventually close upon itself. The black hole simply reveals this flexibility in its most extreme form. One could say, in a quiet metaphor, that a black hole is a place where time folds inward to meet itself, not vanishing, but converging. It is the completion of the trajectory that began with the star's birth, a return of motion into stillness. The equations of relativity describe this as a continuation, not a cessation. The fabric of the universe simply turns inward until the notion of later ceases to have meaning. Understanding this boundary requires a theory that unites the continuous fabric of relativity with the discrete probabilities of quantum physics. Only then can we describe what happens to time when geometry becomes uncertain. This effort has led scientists to explore several paths, from string theory to loop quantum gravity. The latter, in particular, offers a picture in which space-time is composed of finite, interconnected loops that resist infinite compression. In this framework, the singularity dissolves into a region of extreme but finite curvature, and time, rather than ending, undergoes a transition dot to explore this possibility. We now turn to the next chapter, to the quiet frontier of modern physics, where gravity becomes quantum, and the end of time may instead become its rebirth. When general relativity reaches the singularity, it stops speaking. The equations that describe curved spacetime cease to give finite answers, and all predictions dissolve into infinities. For many decades, physicists have looked for a language capable of going further, one that could describe gravity when space and time themselves become quantum objects. Out of this search emerged several candidates. And among them, one of the most conceptually elegant is loop quantum gravity, a framework that tries to quantize space-time directly, without invoking extra dimensions or hidden entities. Loop quantum gravity begins with the insight that if all matter and energy show quantum behavior, then geometry must do the same. Space cannot be perfectly continuous. It must consist of discrete units, just as light consists of photons. In this view, the smooth fabric of space-time that Einstein described is an approximation, valid only at scales much larger than the fundamental quantum of area and volume. At scales near the Planck length, about 10 to the minus 35 meters, space becomes granular, composed of tiny interlocking loops that form a vast network. This structure, called a spin network, represents not matter inside space, but space itself. Each link carries a quantum of area. Each node carries a quantum of volume. Together, they weave the geometry of the universe. Unlike string theory, which describes fundamental objects moving in a fixed background, loop quantum gravity eliminates the background entirely. Space is no longer a stage. It is the ensemble of relationships between the loops. Geometry is not laid down beforehand, but arises from the way these loops connect. In a sense, the universe builds itself from the inside out, each quantum of space defining its neighbors through mathematical adjacency rather than position in a grid. Time, in this framework, is not an external parameter, but an ordering of changes within this network. The flow of time is replaced by evolution of connections. When applied to black holes, this approach produces striking consequences. Because the loops have finite size, space cannot collapse indefinitely. The density of matter reaches a maximum value determined by the quantum of area, beyond which further compression is impossible. The singularity of classical relativity is replaced by a region of extremely curved but finite geometry, sometimes called a Planck star. Within that region, quantum pressure generated by the discrete nature of space counteracts further collapse. In mathematical terms, the equations of loop quantum gravity modify Einstein's equations with corrections that become significant only at Planck scale densities, turning what was an endpoint into a transition. These corrections suggest that the interior of a black hole might not be a dead end, but a bridge to another region of spacetime. Instead of ending at infinite curvature, the collapsing matter could undergo a quantum bounce, re-expanding on the other side. The process would be smooth from the standpoint of quantum geometry, even though it would appear instantaneous in classical coordinates. This possibility links the death of stars to the birth of new domains of space, echoing the way cosmologists describe the early universe. In some models, the Big Bang itself could be such a bounce, the rebound of a previous contracting universe through a phase of quantum. Gravity.loop quantum gravity offers a consistent framework for exploring these ideas because it treats space-time and matter as aspects of the same network. The gravitational field is not something separate from geometry. It is geometry. The quantum state of the universe is therefore a superposition of possible geometries, each with its own arrangement of loops. At ordinary scales, these possibilities average out to produce the familiar, continuous world, but near extreme curvature, the granularity becomes evident. The same discreteness that prevents a singularity also defines the smallest units of area on the event horizon. From this quantization arises a natural explanation of a black hole's entropy. The horizon surface can be thought of as made of finite patches, each representing a quantum of information. Mathematically, the entropy computed in this way matches the Bekenstein-Hawking formula, reinforcing the idea that information is encoded on the surface, not lost in the interior. This connection between loop quantum gravity and thermodynamics strengthens the hope that the theory is capturing something essential about nature. The area of the horizon measures not only how much matter has fallen in, but also how many quantum configurations the underlying geometry can take. The more surface patches, the higher the entropy, and the more ways the interior can arrange itself while preserving the same external mass and spin dot at its heart. The theory replaces the smooth continuum of space with a combinatorial structure. Instead of continuous coordinates, there are relationships between nodes and links. Instead of fields spread everywhere, there are quantized excitations defined by the network. When curvature increases, those relationships shift, producing what we perceive as gravity. The universe evolves as these connections change, and time, in turn, is the record of their evolution. In this picture, time does not end at the singularity because the network never collapses to a point. It may contract to its minimal configuration, pause, and then reconfigure into a new branch. The end of one history becomes the beginning of another. Although these ideas are mathematically rigorous, they remain beyond experimental verification. The Planck scale is far smaller than anything we can currently probe, and the interior of a black hole cannot be accessed directly. Yet indirect hints appear in various corners of physics. Cosmological models based on loop quantum gravity predict specific patterns in the early universe's background radiation, and numerical simulations show how quantum corrections can resolve classical singularities without violating known physics. Each result suggests that the universe may be self-consistent down to its smallest scales. If confirmed, this would mean that black holes are not places of destruction, but of transformation. They would act as cosmic recyclers, converting collapsed matter into new geometric configurations. The information paradox would find a natural resolution. Information would not vanish, but reappear, encoded in the network that emerges after the bounce. The event horizon, in this sense, would mark not a loss, but a delay, a point where information is stored in quantum geometry until conditions allow it to emerge beyond its specific predictions. Loop quantum gravity carries a deeper philosophical implication. It suggests that reality is fundamentally relational. What exists is not objects in space, but the links that connect them. Geometry, matter, and time are all manifestations of these relationships. The world is not made of things but of interactions, an idea that harmonizes with quantum theory's probabilistic nature and with relativity's geometry of interdependence. One could say, in a single soft metaphor, that loop quantum gravity paints the universe as a vast woven fabric, where each thread is both independent and inseparable from the rest. A fabric may bend, stretch, or fold, but it never tears into nothingness. Even the deepest collapse becomes a rearrangement of pattern. In this sense, the black hole's core is not a void, but the most intricate knot in that weave, a place where geometry ties itself so tightly that new structures are born from the tension. Research continues to refine this picture. Efforts to merge loop quantum gravity with quantum field theory, to connect it with thermodynamics and holography, and to derive measurable consequences for gravitational waves and cosmic background signals are ongoing. Whether or not it proves to be the final theory, it represents a vital step, a demonstration that the laws of physics need not break at the limits of relativity. The infinities that once marked the end of understanding become signposts, guiding us toward a more complete description of nature. As we leave this domain of quantum geometry, another theoretical consequence emerges from the equations. If a collapsing black hole can bounce, producing an outflow of matter and energy, What would such a phenomenon look like from the outside? Could the universe ever reveal the mirror image of a black hole, an object where nothing can enter, only leave? To explore that idea, we turn next to the speculative but fascinating concept of the white hole, a theoretical reflection of collapse that shows how gravity might behave in reverse. Among the most fascinating and least understood predictions of general relativity is the idea that for every black hole, there could exist a mirror image, a region of spacetime where the rules of motion and time are reversed. While a black hole is a place from which nothing can escape, a white hole is, in theory, a place into which nothing can enter. Matter and energy can only emerge from it, never cross its boundary inward. The concept sounds abstract, but mathematically, it arises naturally from the same equations that describe black holes. In the formal symmetry of relativity, reversing the direction of time in a black hole solution produces a white hole. The first to recognize this symmetry were mathematicians exploring the complete extension of the Schwarzschild solution, which describes a non-rotating black hole. In that extension, the geometry of spacetime includes not only the familiar exterior region and the black hole interior, but also a second region, one that appears to be the time reverse of the other. In the black hole, particles fall inward through the event horizon and cannot return. In the white hole, particles are expelled outward through a similar horizon and cannot enter. Both share the same mathematical structure, but the arrows of time point in opposite directions. This duality reveals one of the most elegant aspects of general relativity. The equations themselves do not prefer a direction of time. They are symmetric. If one solution represents collapse, its mirror represents expansion. In practice, however, the universe we observe is not symmetric in this way. We see stars collapsing, not spontaneously ejecting matter from nowhere. The apparent absence of white holes in nature suggests that while the mathematics allows them, the initial conditions of our universe do not. Yet, this asymmetry raises questions about why time seems to have a preferred direction, and whether that preference emerges from deeper physical principles rather than the equations themselves. A white hole, if it existed, would appear as an object emitting matter and radiation, but refusing to absorb any. To an external observer, it would look similar to a black hole in its gravitational field, but its behavior would be radically different. Instead of drawing material inward, it would continuously expel it like a cosmic fountain. Anything approaching its event horizon would be pushed away by the geometry of spacetime itself. In this reversed region, the gravitational field would still curve light and influence orbits, yet nothing would ever cross the horizon inward. The process would violate no physical law in relativity, but it would contradict our experience of entropy and causality. For this reason, white holes are usually regarded as mathematical artifacts rather than real astrophysical entities. Still, the concept has persisted because it may point toward deeper symmetries in nature. In some extensions of general relativity, and in certain models of quantum gravity, white holes could represent the other side of black holes, not separate objects, but connected regions of a single geometry. If space-time can bend and reconnect in higher dimensions, the interior of a black hole might tunnel into a white hole region through a quantum process. The matter that falls into the black hole would eventually emerge from the white hole, though not in any recognizable form or time frame. In this scenario, the black hole's slow evaporation through Hawking radiation could be viewed as the distant, gradual appearance of its white hole counterpart. Loop quantum gravity provides a framework in which this transformation can be made explicit. Because the theory replaces the classical singularity with a finite quantum region It allows for a continuous transition from collapse to expansion. The collapsing geometry contracts to its minimum volume, then bounces outward, forming what appears, from the outside, as a white hole. In such models, the black hole is temporary. It evolves through an intermediate quantum phase and re-emerges as an expanding region that releases the information and matter previously trapped inside. The timescale for this process, measured from the outside, could be vast, possibly longer than the current age of the universe, but finite nonetheless. This view transforms the traditional image of a black hole as a final endpoint into that of a dynamic participant in cosmic evolution. The collapse of matter would no longer signify annihilation, but reconfiguration. The geometry of spacetime would recycle itself, turning gravitational death into gravitational rebirth. The information paradox, which once seemed insoluble, finds a natural resolution. Nothing is truly lost, only transformed and delayed by the curvature of spacetime. The white hole becomes the mirror through which information re-enters the universe. Restored from the quantum depths of the black hole interior, the idea of white holes also resonates with cosmology on a larger scale. Some researchers have proposed that the Big Bang itself might have been a kind of white hole, the time-reversed counterpart of a collapsing black hole in another universe. In this view, what we call the beginning of time could be the continuation of a process that began elsewhere, in a collapsing phase whose interior geometry gave rise to our own expansion. The matter and energy of our universe would then be the outflow of that earlier collapse, emerging through a horizon that marked the birth of space and time. While speculative, this hypothesis connects the smallest and largest scales, linking black holes to the origin of the cosmos itself. Observationally, no confirmed white hole has ever been detected. Some phenomena, such as gamma-ray bursts or unexplained fast radio signals, have occasionally been suggested as possible manifestations, but none fit the theoretical expectations precisely. If white holes do exist, they might be extremely short-lived, appearing only as transient events during the final evaporation of black holes or in the earliest moments of the universe. Detecting them would require observing signatures of matter suddenly emerging from empty space, a challenge at the limits of both technology and imagination. Despite their uncertain status, white holes serve an important role in theoretical physics. They remind scientists that the equations governing gravity are broader than our current reality, that time reversal and energy symmetry remain mathematically possible even if not observed. In exploring these possibilities, researchers test the consistency of fundamental principles: energy conservation, causality, and the second law of thermodynamics. Each of these laws must be re-examined when confronting extreme space-time geometries. White holes act as thought experiments, stretching the boundaries of what physics can describe without breaking its internal logic. In a quiet metaphor, one might think of the white hole as the universe's exhale, the complementary motion to the black hole's inhale. If a black hole gathers and conceals, a white hole releases and reveals. Together, they complete a cycle that mirrors the balance found in many physical systems: compression and expansion, absorption and emission, collapse and rebirth. Whether or not this symmetry exists in reality, it helps us understand that gravity is not merely a force of binding, but also a process of transformation. Modern theories continue to explore how this symmetry might manifest. Some versions of quantum cosmology envision networks of black and white holes connected through the fabric of the universe, exchanging matter and information across immense distances and timescales. In such a vision, the cosmos becomes a vast web of transitions, each region undergoing cycles of collapse and expansion. Black holes seed white holes. White holes give rise to new regions of space. Though speculative, this picture carries a certain consistency. Nothing truly disappears. And the architecture of reality sustains itself through change. Ultimately, whether white holes exist as physical entities or remain only mathematical reflections, they illustrate an essential truth about theoretical science, that the universe is always more symmetrical in principle than it appears in observation. Our task is to discover which of those symmetries the cosmos has chosen to express. In doing so, we expand not only our models, but our sense of what is possible. From this exploration of mirrored geometry, we turn next to a more grounded question, not of what could exist, but of what we already know does. Black holes are not merely theoretical curiosities. They are fundamental actors shaping the evolution of galaxies, stars, and even the large-scale structure of the universe itself. To understand their true role, we must look outward again, from the deep equations of relativity to the cosmic landscape that surrounds us. For much of the 20th century, black holes were thought to be rare curiosities, theoretical remnants of collapsing stars. Fascinating to mathematicians, but irrelevant to the large-scale workings of the cosmos. That view has changed completely. We now know that black holes are not isolated accidents, but fundamental components of galaxies. Engines that shape their evolution, regulate their growth, and influence the distribution of matter on cosmic scales. They are both destructive and creative, feeding on the gas and stars around them while driving winds, jets, and radiation that sculpt the space beyond. Far from being exotic exceptions, they are essential to how the universe organizes itself. Every large galaxy we have observed appears to contain a supermassive black hole at its center, with masses ranging from millions to billions of times that of the Sun. These central objects are not mere byproducts of galactic formation. They participate actively in it. The relationship between the mass of a galaxy's central black hole and the velocity of the stars in its bulge, known as the M-sigma relation, shows that galaxies and their black holes grow together. When the black hole accretes matter, it releases enormous energy in the form of radiation and high-speed particles. This outflow heats and disperses surrounding gas, preventing new stars from forming until the environment cools again. In this way, black holes act as regulators, balancing creation and restraint within galaxies. The most powerful expressions of this process are active galactic nuclei and quasars, where supermassive black holes consume matter at extraordinary rates. As gas spirals inward through the accretion disk, friction and magnetic turbulence convert gravitational energy into heat, producing luminosities that can outshine entire galaxies. The light we see from quasars often comes from regions smaller than our solar system, yet their energy output can exceed that of hundreds of billions of stars. Observations of distant quasars reveal that these objects were common in the early universe, suggesting that black holes played a major role in shaping the first generations of galaxies. The radiation and jets they emitted may have influenced how gas cooled, how stars formed, and how the large-scale structure of the cosmos emerged. The presence of supermassive black holes is not limited to the centers of galaxies. Intermediate mass black holes, between a few hundred and a few thousand solar masses, have been found in dense star clusters, perhaps serving as seeds for future growth. Stellar mass black holes, formed by the collapse of massive stars, are scattered throughout the Milky Way, often in binary systems where they accrete material from a companion. The gravitational waves detected by the LIGO and Virgo observatories since 2015 have confirmed that such black holes frequently merge, releasing bursts of energy that ripple through spacetime. These observations have transformed our understanding of black holes from theoretical constructs into tangible astrophysical phenomena. We now hear their presence across the universe in the form of gravitational signals that stretch and compress the fabric of reality itself, dot at the centers of galaxies. Black holes also power immense relativistic jets, narrow beams of plasma accelerated to near the speed of light. These jets can extend for thousands of light years, carrying energy and magnetic fields far beyond the galaxy's core. They interact with intergalactic gas, heating and compressing it, sometimes triggering new bursts of star formation while suppressing it elsewhere. The combined effect of radiation and jets is known as feedback, and it is essential in modern models of galaxy evolution. Without it, simulations predict galaxies that are too massive, too dense, and too full of stars compared to what we observe. The activity of black holes therefore provides the self-regulating mechanism that keeps cosmic growth in balance. On smaller scales, black holes affect their immediate neighborhoods in subtle but measurable ways. The orbits of stars near the Milky Way's center, for example, trace the gravitational pull of Sagittarius A*, a supermassive black hole containing about 4 million solar masses. Decades of precise observation by astronomers such as Andrea Ghez and Reinhard Genzel have mapped these stellar orbits in exquisite detail, providing direct evidence of the black hole's existence. When material occasionally falls toward it, Sagittarius A* emits brief flares of X-rays and infrared light, reminders that even a relatively quiet black hole remains dynamic. Its surroundings shaped by infalling matter and magnetic turbulence. The influence of black holes also extends to the chemical evolution of galaxies. By driving outflows of gas, they help distribute heavy elements created in stars into intergalactic space, enriching future generations of stars and planets. In this way, the processes associated with black holes indirectly contribute to the conditions necessary for life. The carbon, oxygen, and iron that make up our world may have been spread through space by winds and jets originating from galactic nuclei long ago. What once seemed purely destructive is thus deeply connected to creation. Beyond individual galaxies, black holes may play a role in large-scale structure formation. Their energy output during the quasar era likely influenced the temperature and ionization of the intergalactic medium, affecting how clusters of galaxies formed and how matter aggregated into the cosmic web we see today. Some cosmologists even suggest that primordial black holes, formed shortly after the Big Bang from density fluctuations, could account for part of the universe's dark matter. Although evidence remains uncertain, such black holes would have masses ranging from that of small asteroids to that of stars. Invisible unless they pass close. Enough to distort background light through gravitational lensing. The study of black holes has therefore evolved from speculative mathematics into a central pillar of astrophysics. They provide laboratories for testing general relativity under extreme conditions, for probing quantum effects near horizons, and for measuring the limits of energy conversion. The first image of a black hole's shadow, captured in 2019 by the Event Horizon Telescope, offered direct visual confirmation of relativity's predictions. The ring of light surrounding the shadow matched calculations with remarkable accuracy, showing that even at the edge of the observable universe, the geometry of space behaves as Einstein described. Each such observation brings the abstract closer to the tangible, turning theoretical predictions into direct experience. In a gentle metaphor, one might think of black holes as the heartbeat of galaxies, invisible centers whose gravity and energy set the rhythm of cosmic evolution. They pull matter inward, release radiation outward, and maintain balance across unimaginable scales. Their silence defines structure. Their hunger drives creation. Through them, the universe demonstrates a kind of dynamic equilibrium, where even destruction serves the continuity of form. What makes this understanding profound is that it connects opposites. Black holes, which erase local detail, generate the very complexity of galaxies. They regulate life cycles of stars, influence the distribution of elements, and perhaps even seed the conditions for consciousness to arise billions of years later. In the vast chain of cause and effect that links the cosmos, black holes stand not as dead ends, but as pivotal nodes, points where the laws of gravity, thermodynamics, and quantum mechanics converge to sustain the universe's long-term balance as our instruments improve. We will continue to uncover how intimately black holes are woven into the cosmic fabric. We will detect smaller mergers, map faint jets, and measure the spin of distant quasars. Each discovery will refine our picture of how galaxies breathe, grow, and age. Already, the line between astrophysics and philosophy begins to blur. When we study black holes, we are also studying the architecture of reality itself, how order arises from collapse, and how meaning persists in the absence of light. From this broader view, the next step is almost inevitable. Having seen how black holes shape the universe outside them, we can now ask what they reveal about the deeper nature of existence, about space, time, information, and the human attempt to understand. The next section turns to that reflection, how black holes, once symbols of oblivion, have become windows into the fundamental nature of reality. In studying black holes, physics approaches its own philosophical frontier. These objects are more than regions of space where gravity has triumphed over all other forces. They are experiments set by nature at the limits of knowledge. They test our theories of matter, time, and causality, exposing the deep connections between them. What began as a mathematical prediction in Einstein's equations has become a real, observable phenomenon, and yet one that still resists complete understanding. Through black holes, we learn not only about the structure of the universe, but about the structure of our understanding itself, not at first glance. Black holes seem to represent the ultimate separation between what is real and what can be known. The event horizon divides the universe into two domains, the observable exterior and the unreachable interior. According to relativity, information cannot cross from inside to outside. No light, signal, or causal influence escapes. Yet quantum mechanics, which governs everything at microscopic scales, insists that information cannot be destroyed. This contradiction forces us to reconsider what we mean by reality. Is the universe defined by what can be observed, or does it include what exists beyond observation? The black hole sits precisely on that boundary, making visible the tension between the measurable and the unknowable. The debate about information has gradually evolved into a broader insight. Reality itself may be relational. In modern physics, what exists is not absolute objects, but the relationships between them, the ways in which one system influences another. The black hole's event horizon embodies this principle. From the outside, the horizon behaves like a physical surface, encoding information about everything that has fallen in. From the inside, it is not a barrier at all. The infalling matter passes freely. Each perspective is valid in its own frame, and the complete description requires both. This duality is not a failure of theory, but a feature of how reality organizes itself, multiple, consistent viewpoints describing the same underlying structure. The holographic principle arises from this realization. It proposes that the information contained within a volume of space can be fully described by data encoded on its boundary. In this sense, the universe behaves like a hologram, a three-dimensional image projected from a two-dimensional surface. For black holes, this means that everything that happens inside can be represented by quantum states living on the horizon. Gravity and space emerge from the organization of this information. If the principle extends to the entire universe, then all of reality, galaxies, stars, and ourselves might be expressions of information inscribed on a distant cosmic boundary. What we experience as depth and distance would then be emergent properties, not fundamental features. This idea unites physics in an unexpected way. Quantum theory, which describes probabilities and information, and general relativity, which describes geometry and gravity, become aspects of the same framework. Space-time would no longer be the backdrop for events, but the result of interactions among quantum bits of information. The curvature of space, the flow of time, and even the presence of matter could all emerge from the collective behavior of microscopic degrees of freedom. The black hole, once a symbol of finality, becomes a clue to the informational architecture of the universe. The implications of this shift reach beyond science. They touch on questions once considered purely philosophical. What does it mean for something to exist? Is space an entity, or merely a relation among events? Does time flow, or is it an illusion created by our perception of change? Physics does not answer these questions in metaphors, but in equations. Yet the equations now point toward a view of the universe that is profoundly interconnected. The boundary between matter and information, between physical and abstract, begins to dissolve. In this view, the universe is not a collection of isolated things, but a self-consistent web of relationships where information and geometry are inseparable. Experimental evidence continues to support this perspective. Observations of gravitational waves confirm that spacetime is dynamic and responsive, capable of carrying energy and information. The Event Horizon Telescope's images of black hole shadows demonstrate that even at their most extreme, the predictions of relativity remain intact. Meanwhile, advances in quantum computing and information theory have revealed deep parallels between entanglement, the correlation of quantum states across distance, and the connectivity of spacetime itself. Some physicists propose that entanglement is literally the glue that holds the universe together. In their equations, the strength of entanglement determines the strength of gravitational connection. Space may be woven from the threads of quantum information. In this sense, black holes are not just astrophysical objects, but conceptual tools. They reveal how gravity, quantum theory, and information interrelate. They show that what we perceive as continuous space may be a large-scale pattern emerging from discrete, informational building blocks. They also hint that consciousness and observation, rather than being external to the cosmos, are part of its informational flow. The observer and the observed are entangled, each defining the other through interaction. This is not mysticism, but the logical consequence of quantum theory applied universally. The act of measurement does not create reality, but participates in it. One can imagine, in a quiet metaphor, that the universe behaves like a grand reflection. Every particle, wave, and event mirrored on the surface of existence. Black holes are the most polished of these mirrors, showing us the symmetry between knowledge and mystery. They remind us that understanding grows not by removing all uncertainty, but by learning how uncertainty itself shapes the world. Beyond the philosophical, the informational view of black holes also provides practical tools for physics. By studying how horizons store and release information, scientists gain clues toward a quantum theory of gravity. Theories such as string theory, loop quantum gravity, and holographic dualities all attempt to describe how geometry emerges from quantum mechanics. Each offers partial answers, but together they suggest a coherent direction, that reality is fundamentally finite in detail, yet infinite in expression. The black hole, with its surface area quantized in units of Planck's scale, is a laboratory for testing these ideas. It turns metaphysics into measurement. Perhaps the most striking outcome of this research is the redefinition of nothingness. Classical physics imagined the vacuum as empty, a stage without content. Modern physics shows that the vacuum is alive with potential, a sea of fluctuations, virtual particles, and hidden correlations. Even a black hole's darkness is filled with structure. Its horizon vibrates with quantum degrees of freedom. Its interior geometry encodes histories of matter that once fell in. There is no true void, only regions of reduced visibility. The universe, it seems, wastes nothing, not even silence. Understanding black holes thus reshapes our understanding of ourselves. The same laws that govern the collapse of stars govern the particles in our bodies. The same information that defines space and time defines the processes of thought and memory. We are not separate from the cosmos, but expressions of it, built from the same informational principles that govern its largest structures. To study black holes is, in a sense, to study our own origin and destiny. This recognition brings a sense of coherence to the apparent complexity of nature. Across scales, from quantum particles to cosmic structures, the same principles apply. Energy and information are conserved. Geometry responds to mass and motion, and patterns repeat in self-similar ways. Black holes reveal the unity behind these patterns. They transform chaos into order, destruction into renewal, and isolation into connection. Their presence in the universe is a constant reminder that simplicity and depth coexist at every level dot as we look forward. The next frontier will not be about what lies inside black holes, but about what remains after we have learned from them, what they ultimately tell us about existence itself. The final section of this journey will bring together all that has unfolded so far: gravity, time, information, and meaning. We will ask what remains when light, matter, and even knowledge reach their limits, and what the silent presence of black holes reveals about the enduring harmony of the cosmos. After every calculation, every theory, and every image, one question remains: what does a black hole finally leave behind? When the equations have been solved, when the radiation has faded, and when the curvature has smoothed into the quiet fabric of expanding space, what endures of the immense process we have traced? In this final reflection, we move beyond specific mechanisms to the larger meaning they reveal, not in poetry, but in structure, not in speculation, but in continuity. When a black hole evaporates through Hawking radiation, its mass decreases, its temperature rises, and its radiation accelerates. Over unimaginable timescales, the event horizon contracts until the object becomes microscopic, emitting its final burst of high-energy particles. The total energy released equals the mass that once fell in. Nothing is lost. Energy, momentum, and angular momentum are conserved in the outward stream of quanta. Yet what of the information that defined the black hole's interior? Modern quantum gravity models suggest that it too is preserved not as recognizable matter, but as correlations imprinted on the outgoing radiation. In that sense, what remains is not the object, but the record of everything it ever contained. As the last photons drift into space, they carry with them the memory of the black hole's existence. Over vast distances, Those particles become part of the cosmic background, indistinguishable from the radiation left by other processes. The universe absorbs the trace without waste. Matter has become energy. Geometry has become information. The cycle is complete. On the grandest scales, the death of black holes merges with the slow cooling of the cosmos. Long after the last stars have burned out, black holes will persist as the final luminous agents, evaporating one by one until only the faint echo of their radiation fills an otherwise dark universe. In this ultimate era, sometimes called the black hole epoch, the universe will be a diffuse sea of particles and low-frequency light, expanding endlessly. Gravity will no longer gather matter into galaxies. Thermodynamics, not mechanics, will define the cosmic landscape. The black holes that once powered quasars and anchored galaxies will have dissolved into quantum fields, and their energy will be dispersed so evenly that no region will differ from another. The cosmos will reach its maximum entropy, the state of equilibrium where change continues, but meaning in the human sense of contrast no longer applies. This is not annihilation, but balance, a natural end of processes, driven by the same laws that once formed the first stars. Seen from this perspective, black holes are not anomalies, but mediators of cosmic order. They transform structure into equilibrium, ensuring that the universe evolves toward uniformity. Their formation, activity, and eventual evaporation represent the full arc of physical law, from gravity's concentration of matter to quantum mechanics' dispersal of energy. The story of the black hole is therefore the story of how the universe preserves consistency while allowing complexity. Each collapse is followed by emission, each confinement by release. The apparent finality of the horizon hides a perfect continuity of exchange. Understanding this cycle has altered how science conceives of permanence. In classical thought, things existed or they did not. They began and ended. Modern physics shows a subtler pattern. Everything transforms, but nothing truly disappears. Energy changes form, information changes medium, geometry changes curvature. The conservation laws that underlie these transitions guarantee that the total content of the universe, its information, energy, and causal structure, remains constant even as its appearances shift. What remains after a black hole has vanished is not emptiness, but conservation itself. The persistence of pattern through transformation. This realization also reframes the human position in the cosmos. The same principles that govern the evolution of black holes govern our own material existence. The atoms in our bodies were forged in stellar cores. The energy that sustains us once moved through cycles of fusion and decay that follow the same thermodynamic laws. When those atoms eventually return to interstellar space, their information continues in new combinations. On the most fundamental level, we are part of the same continuity, temporary configurations of universal order, subject to its transformations, but never outside them. The study of black holes has therefore become a kind of mirror for knowledge itself. Each advance in observation or theory extends the boundary of what can be known, yet always leaves a horizon beyond which questions remain. In that way, the event horizon is not just an astrophysical surface, but an epistemological one, a limit that recedes as we approach it, guiding inquiry without ever vanishing. Science advances precisely by touching those horizons, redefining the edge of understanding while accepting that an edge will always exist. One might say, gently, that the silence surrounding black holes is not emptiness, but invitation. Their absence of light is filled with the promise of explanation. Their darkness with the data that emerge when we listen in different ways, through gravitational waves, radio interferometry, and mathematical analysis. The universe speaks quietly, and black holes are its most disciplined language. They compress complexity into simplicity, reminding us that elegance and mystery are not opposites, but partners in description. The ultimate lesson of this journey is coherence. From quantum fluctuations to galactic evolution, the same principles sustain every scale: conservation, symmetry, and the tendency toward equilibrium. Black holes illustrate these principles with unmatched clarity. They transform motion into geometry, information into horizon area, and collapse into radiation. Each transformation is reversible in the larger sense, ensuring that the universe as a whole remains self-consistent. The more we understand these transformations, the less the black hole seems like a tear in reality, and the more it appears as its confirmation, the point where the universe demonstrates the completeness of its own design. Modern astrophysics continues to test this completeness. Future space telescopes will observe the dynamics of event horizons with finer resolution. Gravitational wave detectors will trace the merging of intermediate mass black holes. Theoretical work will refine how information flows across horizons. Each step brings us closer to describing the universe without contradiction, uniting quantum mechanics and relativity in a single language. The pursuit may never be finished, but its direction is clear. The universe is knowable. Through the patterns it repeats. As we reach the close of this exploration, the black hole no longer stands as a symbol of destruction, but as an emblem of continuity. It gathers, releases, and balances, shaping galaxies, driving energy across scales, and revealing the link between matter and information. What remains after the equations and the observations is a simple truth. The universe conserves its meaning as faithfully as it conserves its energy. Change is constant, but loss is illusion. In the faint future, when the last black hole completes its evaporation, the universe will be quiet but not empty. Its silence will contain every vibration that has ever existed, stretched into wavelengths too long to detect, but still present in the background of being. The cosmos will not have ended. It will have reached equilibrium, a state where all histories coexist as information distributed perfectly through space. In that distant calm, the legacy of black holes will persist as structure without contrast, energy without form, and knowledge without observer. And so the story returns to its beginning. The question of what happens inside a black hole becomes the question of how reality maintains itself at its limits. The answer, emerging slowly through decades of science, is both simple and profound. Nothing truly vanishes. Gravity, quantum mechanics, and time together ensure that existence is continuous, even when it appears to collapse. The silence of the black hole is therefore not the end of the universe's voice, but the pause between its phrases, a reminder that every end is part of an ongoing sentence, written in the geometry of space-time. Thank you for spending this quiet time with Calm Science Sleep. May your thoughts settle and your curiosity rest gently on what you've just discovered. If this peaceful science helped you unwind, please subscribe, like, and share your thoughts in the comments. It helps new listeners find us and keeps me inspired to craft more calm explorations. Join us again soon for another soft journey through the quiet wonders of the universe.